In this second video, I will introduce two more rules for calculating probabilities. Just as we saw at the end of the previous video, there is a general rule for calculating conjunctions, regardless of whether the conjuncts are independent. Now, this next rule I'll give you now is a general rule for calculating the probability of disjunctions, regardless of whether the disjuncts are mutually exclusive. So as very quickly, the rule I gave you last week simply said when you know the disjuncts are mutually exclusive, when you know the disjuncts logically cannot be true together, then you can calculate the probability of the disjunction by simply adding up the probability of the disjuncts. But now, in general, to calculate the probability of a disjunction, you add up the probability of the disjuncts and then you subtract the probability of their conjunction, the conjunction of the two sentences, which are the disjuncts in the original sentence you care about. Then this rule can help us calculate the probabilities of disjunctions regardless of whether the disjuncts are mutually exclusive. So for instance, an example of mutually exclusive disjuncts are, let's say that you're drawing cards randomly from a deck. Now, every card has a suit and no card has multiple suits. So the probability of drawing either a clubs or a hearts, because those two possibilities, drawing a clubs or drawing a heart, because those are mutually exclusive, you can simply apply the rule, simple rule from last week, where you simply add up the probability of drawing a clubs with the probability of drawing a heart. And that's how you calculate that kind of disjunction. But there's other things we might care about where the disjuncts are not mutually exclusive. For instance, you might wonder about the probability of, for instance, with a card deck, you might wonder what the probability of drawing a jack or a clubs. And in the case we just saw a second ago, where we were wondering whether the probability of drawing a clubs or hearts, those two possibilities are mutually exclusive because there's no card that is both a clubs and a hearts. But in the case I just gave, jack or hearts, I think, in that case, there are cards which are both a jack and a hearts. And in particular, there's one card, there's a jack of hearts. So the possibility of drawing a jack or drawing a hearts, those are not mutually exclusive possibilities. So you cannot calculate the probability of drawing a jack or a hearts by simply adding up the probability of drawing a jack and the probability of drawing a hearts. What you have to do is you add those up and then you subtract the probability of drawing both a jack and a hearts, i.e. the probability of drawing the jack of hearts. So you have to subtract their overlap. Now, I'm just going to very quickly discuss the diagram in the textbook, which very intuitively and clearly explains how this rule works. And it also explains why this rule can be applied when the disjuncts are nonetheless mutually exclusive. That is to say, it explains how the simple rule is a special case of this general rule. Okay, so we saw a similar diagram in the previous lecture when I talked about conditional probability. And as with that diagram, I want you to think of the space that A's circle occupies as the amount of probability that A has. Okay, so we're wondering about the probability of A or B. Okay, so what we're wondering about is what is the overall space that A and B take up? Okay, because we're wondering about the probability of the truth being either A or B. So what is the overall probability of all of this space when we combine A and B together? Now this purple region is the overlap of A and B. That is, the space of this purple region is the probability of the conjunction A and B. So as we see here, if you want to know the probability of A or B, of the overall region that A and B takes up, we have to add up the purple region in the middle, which is the overlap between A and B. It's the probability of A and B. We have to add that up with the red and the blue region. So here we see that the probability of A or B, or the A or B region, is the red part, the purple part, and the blue part. So the red part is the region of A that's not B. This is a part of A that does not overlap with B. The blue part is a part of B which does not overlap with A. And then the purple again is the A and B region. So if we want to know the overall probability of A or B, this whole region here, we have to add up the red with the purple with the blue. So now if we look at what we have here, what we're doing is adding up the A region, the entire A region, the entire B region, and then subtracting their overlap. So to return to this diagram, what we're doing to calculate the A or B region is we add up the entire A region, including the purple, and with the entire B region, also including the purple. But then what we have to do is subtract their overlap, because if we didn't subtract the overlap, we would be counting the purple region twice. So adding up the red, so the other way it's put here is that adding up the red, the purple, and the blue is the same as adding up the red plus the purple, which is the entire A region, with the blue plus the purple, which is the entire B region, and then subtracting the A and B region. And that's exactly which the general formula we have here. The probability of A, the entire A space, plus the probability of B, the entire B space, minus the probability of their overlap, because we want to make sure that we do not count the overlap twice. So when we simply add up A and B, we do count it twice. So that's why we have to subtract it once. And finally, the reason how this shows how the case where A and B are mutually exclusive, you don't have to subtract this, is that in the case where A and B are mutually exclusive, that is, they cannot be true together, in that case, the probability of their conjunction is 0, because the conjunction of two mutually exclusive propositions is a logical falsehood, it's a contradiction. And a contradiction must have 0 probability. So if we know that A and B are mutually exclusive, then we know that the probability of A and B is 0, and subtracting 0 does nothing. Visually, that's to say that if A and B are mutually exclusive, we know that there's actually no overlap. They'll just be two separate circles that do not touch. In that case, we do not have to subtract A and B. So that's how this is a general rule. And in the case where phi and psi, or A and B here, are mutually exclusive, we can ignore this final part. But in the case where they are not, it's crucial that we do not ignore this final part. It's crucial when we do not know that the disjuncts are mutually exclusive. It's crucial that we do subtract the probability of their conjunction so that we do not count it twice. Now, finally, here is the law of total probability. Now, this law is important and interesting in of itself, but furthermore, as I mentioned at the very beginning of this video, this law is crucial to understand as a stepping stone to understanding Bayes' theorem, which we will look at next class, and which is very important in this unit. So here is the law of total probability. So we have this requirement that the probability of psi is not 0 and not 1, so it lies between, strictly speaking, 0 and 1. And in that case, we can calculate the probability of some other sentence phi by adding up the probability of phi given psi times the probability of psi, and the probability of phi given not psi times the probability of not psi. So if we know the probability of some proposition psi, and we know that it's between 0 and 1, strictly or non-inclusively, then we can use that to calculate the probability, the unconditional probability of any other proposition, if we know the probability of that proposition given psi and the probability of that proposition given not psi. And this law will be incredibly important for solving certain questions involving Bayes' theorem, which we'll see beginning this week. So what I'll do now is walk through the proof of this theorem, because it's very simple. I didn't walk through the formal proof of this theorem because it's very complex, so we had to settle with simply just a visual demonstration of it. But the understanding why the law of total probability holds is actually very simple, so I'll walk through that. But before doing so, I want to know that there is a certain restriction here on that the probability of psi cannot be at either extreme of 0 and 1. This restriction also was important. A similar restriction, was important for the general multiplication rule, which was that psi had the probability of psi to be greater than 0. And the reason why both of these restrictions here apply is because both of these rules rely on the definition of conditional probability. And the definition of conditional probability requires that the probability of psi is greater than 0 because we understand the probability of phi given psi as a fraction where the probability of psi is on the bottom. And a fraction, as we know from simple mathematics, is undefined when the denominator is 0. So because we have this conditional probability that the proposition being conditioned on must have a greater than 0 probability, that condition echoes out into our understanding of the general multiplication rule, as well as into our understanding of the law of total probability. But this shouldn't really worry you too much, because in the questions I ask you, I will not be asking any trick questions which involve you understanding whether the probability of psi is greater than 0, or in this case, greater than 0 and less than 1. Okay, but to proceed with the kind of formal proof of why this law holds, the first thing we note is we appeal to the rule that says that logically equivalent propositions have the same probability. So I want you to note that, and this was a result that we looked at in the last unit on deductive logic, a sentence phi is logically equivalent to the following disjunction: phi and psi, or phi and not psi. So the sentence phi and the sentence phi and psi, or phi and not psi, are logically equivalent. And this is something you can prove with the truth table. And I had you do that at a couple of points in the previous unit. Now, and then given that phi is logically equivalent with phi and psi, or phi and not psi, that entire sentence here, we can apply the rule that says that logically equivalent propositions have the same probability to know that the probability of phi equals the probability of phi and psi, or phi and not psi. Then, by the specific additivity rule, we can unpack the probability of this disjunction, because we know that the sentence phi and psi is mutually exclusive with the sentence phi and not psi, because phi and psi is claiming that phi is true, and phi and not psi is claiming that not psi is true. But it cannot be both the case that phi is true and psi is true and not psi is true. So that means that phi and psi, this sentence here, is mutually exclusive from phi and not psi, the other disjunct. So therefore, the probability of the disjunction is simply the sum of the probability of the disjuncts. So once we reach the second step here, we then apply the general multiplication rule to both of the probabilities of the conjunctions of interest, because we're not assuming here that phi and psi are independent. So we have to apply the general multiplication rule, which also requires the assumption here. But I won't go into detail about that. In any case, what we've done is to move from the second step to the third step, and which is the final step. We simply apply the generalized multiplication rule to both of these probabilities of conjunctions. And that's how we derive the result that the probability of phi equals the probability of phi given psi times the probability of psi plus the probability of phi given not psi times the probability of not psi. And this can be applied, as you'll see, when you start working through some of the examples. In many cases, we'll know all of these probabilities from the example, and we'll be able to put them together to calculate the probability of phi. So I now conclude this video and the lecture by giving, just briefly talking about the visual justification of this law. And this is again from the textbook where we have a handy diagram. So again, A, the space that A takes up, is representing the amount of probability that A has. And what's in question here is the probability of phi, the unconditional probability of phi. So let's imagine that A is phi. So we're wondering about how much space A takes up. And what we note is that the size of the A region is the sum of the A and B region, which is the part of A that is red, and the sum, the A and B region is the purple part, right? So the part where both A and B are true, which is the A and B region, and then the A and not B region is the red part, where A is true and B is false. So the sum of A, this whole circle here, is the purple part added to the red part. Okay, so purple plus red. And each of these regions, the A and B region and the A and not B region we saw in this second step, can be calculated with the general multiplication rule, which is that when you have regardless of whether the conjuncts are independent or not, their conjunction can be calculated by looking at the conditional probability of one given the other and the unconditional probability of the other. So that is to say that you can think of the purple region as the amount of B that A takes up, and then you can think of the red region as the amount of not B, which is everything outside of B's circle, this entire red and white space. That's the not B region because B is inside the B circle, so not B is everything else. And you can think of the red region as the amount of not B that A takes up. And then you sum up the amount of B that A takes up and the amount of let me repeat that. You sum up the amount of B that A takes up with the amount of not B that A takes up, which is just the purple part and the red part, and that gives you the overall probability of A. So now in the next lecture, when we start applying Bayes' theorem, we will also see how to apply this theorem here to calculate probabilities, because this theorem is essentially a part of Bayes' theorem, as will become clear.